This is the fourth video in a series of videos about basically how to plan a math unit. And I've been using as my example how I might teach systems of equations. And at this point, there's been 6 lessons. I'm just planning the sequence now. I haven't really planned a full lesson, but at least I now know what's gonna happen. The first day was things like x plus 2y equals 12, just understanding systems of equations and what a solution set might be for that. The second lesson was graphing equations that have 2 variables in them, but keeping it to ones where one of the variables has a coefficient of 1, so I'll say graphing, and by making a chart. The third day was what happens, I have a new drawing program. What happens if one of the coefficients, neither is a 1? How do we graph those? That one was kind of finding the x and y intercepts. And the fourth day was doing systems of equations by graphing. The fifth day switched to algebraic approach, so it was systems with the substitution method, which only works if one of the equations is of the form y equals, and the other one could be anything. And in this video, we're going to see lesson 7, which is going to be sort of the key one, which is the elimination method. The 8th one is probably going to be also just more elimination method. Things with fractional equations or things where we're going to be rearranging things so that we could use the elimination method. So 7 and 8, I mean, really this whole unit, the big outcome is, can they do systems of equations by elimination? But these other lessons all support it, and they get students opportunity to think mathematically. 9th lesson is going to be word problems. Classic word problems, you know, this many, I buy 2 hamburgers and 5 French fries and it costs $28, and how much would it cost for one? You know, get another piece of information. Kind of contrived questions, but I think students do like answering because they're kind of like riddles. And the 10th day is where I want to, because I haven't mentioned at all that there are systems of equations that have no solution, and that there are systems of equations that have an infinite number of solutions, and why that is. So that's sort of that's the 10-day plan. In this video, we're looking at, see how many we can get in the 30-minute period. So let's look at elimination. Oh, I forgot to mention, I was very proud of lesson number 6, which was some sort of theory to motivate elimination method. And that's a very difficult lesson. It might take 2 days to do that. Depends how long you want to spend on it. Honestly, the first time you teach that, it might not go so well because you'll realize that some things are harder than you thought. But I do think it's worthwhile, that lesson number 6. Not every student may like that lesson, and it might even confuse some students. But it's really important, because to just jump to 7, as most textbooks do, you sort of end up doing something that you don't really know. Am I really allowed to do this? So let's go to lesson 7. So lesson 7, in case you're wondering, Microsoft OneNote wants to charge me more money or something like that. So I'm using a different drawing program now. I'm not that happy about it because I really like Microsoft OneNote. This is bamboo paper. Anyway, so systems of equations. So I would start with systems of equations that already have it so that these two things are opposites. Remember, you make up the answer first, and then that tells you what you need to put after the equal sign. 2 times 4 is 8, plus 3 is 11. 3 times 4 is 12, minus 3 is 9. So we start with ones where if we add them together, the variable drops out, just almost lucky. Then maybe we do one where the x's drop out, just so they don't think that it has to be. 2x minus 3y equals, again, make up whatever your favorite two numbers are. 5, 2 is actually not so good for this one. Let's say 6, 2. So this is minus 12 plus 10 is minus 2, and minus 12 plus 6. Oh, sorry, minus 12 minus 6. So here's one where, again, we can add them together to eliminate something went wrong there. If my answer is 6, 2 minus 12, but that should be negative. And minus 12 minus 6 is minus 18. Oh, but when I add these together, I get negative 2y. I get positive 2y. So I get y equals negative 10, which is not the answer at all. Okay, so something went wrong. If it's really 6, 2, that's negative 12 plus 10 is negative 2. That's true. So the problem must be here. 12 minus 6 is positive 6. No idea what I was thinking there. Okay, so now we get to ones where nothing drops out, but first let's do ones where we could easily make something drop out. So for instance, 3x plus 2y and 5x minus 4y. So I'm doing a set of problems now where these two numbers, well, they are already, one's positive, one's negative, and one of them is a multiple of the other one. So make up a convenient answer. How about 2, 7? 6 plus 14, 20, and 10 minus 28 is minus 18. So we look at this and say, well, we could add these together, but it's going to just end up with a new equation to add to the mix. We want an equation that has no x or y in it. So what we look for is it possible to multiply one of the equations, both sides, by some number so that they would be the same size? So we look for one number being a factor of another. In this case, 2 is a factor of 4. So if I multiply both sides by 2, I get 6x plus 4y equals 40. In lesson 6, I established that multiplying both sides of an equation by the same number does not change the solution set. And now I do have this situation. 11x equals 22. And I would do a whole bunch of those, just recognizing that there's one equation. Only one equation needs to be changed. And then we get to the most complicated type. 3x plus 2y and 5x plus 3y, let's say. So what we have is a situation here where we need to either change these both to 15s, or make one 15 and one negative 15, or change these both to 6s, basically the least common multiple of the two numbers. It doesn't have to be the least common multiple. We'll look at that next. So for this one, again, 8, 1, 24 plus 2 is 26, 40 plus 3 is 43. So in this one, we can multiply the top. So see, I'm putting a lot of people would put parentheses around the entire equation. It's not really mathematically accurate to do that, though plenty of people do that. I'm going to do it like this. if I multiply the top one by 3, if I multiply the bottom, that will make this a 6. If I multiply the bottom one by 2, that will make this a 6, but I'm going to choose to make it negative 2. And that way, oops, I should put the 3. I made a whole big deal about how you gotta do it to both sides, and it's not accurate to just stick parentheses around an entire equation. And now we're back to this situation. Something went wrong. I don't want to look up what went wrong here. You could parse through it and see where, well, I am kind of curious. Let's see. 8, 24 plus 2 is 26. 40 plus 3 is 43. So that's okay. 9, 6. Here's the problem. 3 times 26 is not 56. I don't even know where 56 would have come from. 78. Now, a trick that you could tell the students, so if they're having trouble, it's like so many decisions to make, you could say that you could take this number here, and that's the thing you multiply the top equation by, and take the opposite of this number, or the plus 2, and multiply the bottom equation through by that. If they're looking for like an algorithm, sort of a cookbook method for doing a recipe, that would work. That you might be thinking, well, that's not so good, because what if I have this situation, 3x plus 4y and 2x minus, or I'll say minus, I'll say plus 6y. You might say, well, everyone knows we should turn these both into 12s because we want to use the least common multiple. And it's true, making both 12 is better, and it will work nicely. But if some student wants, and here this time I'll go with 5, 3, a little harder. 15 plus 12 is 27. 10 plus 18 is 28. And you could tell them to put a 6 here and put a negative 4 here. Maybe it's not the best if you're looking for small numbers, but especially if students are using a calculator. 6 times 7, 27 is 134, minus 8x minus 24y minus 112. See if I did this properly. Not looking good for me. 22, so something went wrong. Making a lot of careless errors, but I'm doing this in real time. No editing. It's live. Well, not really live, but it's kind of live on tape, as they say. Don't know what exactly went wrong. I am curious, though. 15 plus 12 is 27. That's okay. 10 plus 18 is 28. That's okay. 18, 24, 6 times 27. Oh, there's the problem. 120 and 42 is 162. Much better. And I would spend a lot of time on this. Definitely a whole day on the substitution, the elimination method. Now, I spent 2 days on elimination. Maybe we do ones where it's like not quite ready for elimination method. These are just, and maybe first convert it. Maybe even ones like this. Y equals 2/3 x plus 1. Y equals 3/4 x minus 2. I would, if I want to use elimination, I certainly could use substitution here. But let's say I want to use elimination. I would tell them to multiply this entire equation through by the denominator of that coefficient, and multiply both sides of this equation by the denominator. Oops, made a mistake. That's a 3. and then rearrange. So you can do a lot with substitution. And I think it's the primary skill of the entire unit, to be able to solve systems of equations by substitution. Actually, it's a good opportunity to revisit the graphing one. Something like 3x plus 2y equals 12 and 5x minus 3y equals 15. And they'll recall, maybe, that when we did the graphing approach, this probably, especially here, probably didn't end up as an integer lattice point, integer coordinates. So this would be a good opportunity to do it with, maybe they could approximate it with graphing, and then they can go ahead and algebraically solve it using elimination. So that would be lessons 7 and 8. Lesson 9 would be word problems. And I like these word problems. In fact, I might have started the whole unit with one of these word problems just to like mess around. You know, there's 50 animals and there's 140 legs, and all the animals either have 2 legs or 4 legs. There are no 3-legged animals in this farm. And how many animals? I mean, you could start the whole unit with that and then revisit it on the 9th lesson. It's up to you. I do kind of like, I do like these riddles, but now we're in a position to say like x plus y is 50. That's x is 2-legged animals and y is 4-legged animals, whereas the leg equation is 2x plus 4y equals 140. And to solve that by system of equations, there's questions involving food, hamburgers and French fries. Maybe you want to go with some more vegetarian option for, you know, the year 2019. It's really up to you, but definitely word problems are kind of fun. Like, I think students feel a sense of accomplishment that they can solve these riddles that maybe on the first day they weren't able to solve. On the 10th day, I would have systems of equations that have no solution. And we want to see, you know, why does it have no solution? Well, certainly if we do the process, we end up with something kind of weird. X plus y equals 10 and minus x minus y equals minus 20. And we end up with 0 equals negative 10. So that's one kind of, it's not really a convincing reason, but it is a weird thing that happened. Graphing approach does give a really good feel why this has no solution, that the lines representing the solution sets are parallel, so there is no intersection point. Now, so there's ones that have no solution. Then there's ones that have multiple solutions. And some people think infinite solutions means every ordered pair satisfies the system, but it's not true. Like 3-1 does not make either of these equations true. So it's not like like this other one had no solution. I don't want you to think that this other type, or have your students think that everything is a solution. No, not everything is a solution to this, but 1,9, if it's a solution to the first, it's also a solution to both. So it's not, I think it is accurate to say infinite solutions, but that's not the same thing as saying it's true for every single pair of numbers, whereas the other situation was true for no pair. This is not true for all pairs, but it's true for more than one pair. Anything that makes the first equation true makes the second equation true, and graphing, well, that happens when the two graphs are the same. So that's sort of mapping out the 10 days. Now let's go more sort of granular. I am interested on the first day in not just doing like what's an equation, what are solutions to something like this, solution sets. There's a chance that might be day 2, so that day 1 can be some kind of setup for the whole unit. And part of me is thinking it would be nice to have some riddles. Riddles of systems of equations that you can do with some kind of logic other than elimination method, substitution method, things like that. I guess here's an example of one. X is hamburgers. I know, I'm sorry for the 1960s style word problem. On the most recent algebra regions, they did burgers and fries. 20, 30 years from now, that won't be the standard thing that you use for food. But it's okay. I was just thinking this. 5 burgers and 2 sets of fries. Let's just say a burger is $3 and fries are $2. So this is 15, that's 19. Check out this question. I really like this as a sort of just thing to, and if I have 5 burgers and 4 orders of fries, 15 and 8. See, I like this. I might not do it with symbols on this day. I'm just talking about burgers and fries. I think this would be an interesting question. Not because they're going to use elimination. No. But because they're going to say, oh, wait, it's the same number of burgers, but this one has 2 more fries. So 2 more fries was a $4 difference. So 1 fries is a $2 difference. And that means that y equals 2. Again, I should say burgers, fries, instead of using the symbols. But that is kind of interesting that you could that you could do certain systems of equations using sort of a logic, saying, oh, well, whatever the burgers are, since the number of burgers are the same, the only difference in these 2 numbers has to come from the difference in the number of fries. Technically, when you do your system of equations, use elimination, that's kind of what happens. Anyway, I just want to mention that in motivating this whole unit, like to sort of bookend it and start with word problems and burgers and fries or whatever else you want to use, and end, at least on the 9th day, with word problems again, sort of revisit them. I think that is a pretty good way to do it. It's in the next video. I'll start like planning an actual lesson, like getting into the nitty gritty of what the lesson plan is going to look like. But for the last few minutes, I think I'm going to show you something that you probably don't know already. I'm going to call it 11. Now, lesson 11. Maybe this gets put in elsewhere, maybe not at all, but it's just maybe something for you to know. That systems of equations have been around for a long time. And I'll show you how they did this in ancient China. See, I study history and math, and I really like to see when these questions first appeared. So let's just say 2x plus 3y, 3x plus 5y. It's just an example. And I'm going to make my answer 2, 4. So 4 plus 12 is 16, and 6 plus 20 is 26. So in ancient China, they had this method for doing this question, where if these 2 numbers were the same number, well, we want to get these 2 numbers to be the same number. I'm going to, if you don't mind, if I make these numbers a little smaller just for the purpose of instruction. So 1, that's 2, plus 6 is 8, and 3 plus 10 is 13. So the idea is 8 times 13, that's the least common multiple, is 104. So if I multiply this entire, both sides of this equation by 8 and both sides of this equation by 13, I get 26x plus 39y equals 80, 104, and 24x plus 40y equals 104. So this is funny because I'm not trying to get these numbers the same. I'm trying to get these the same. Because when they are the same, I could then sort of eliminate that and set these two things equal to each other. 26x plus 39y equals 24x plus 40y. Well, that's still got a lot of variables. But there's no constant now. If you rearrange, you move the 24x's over, you get 2x is equal to y. So there's a relationship between x and y. Then you can, if 2x equals y, you could then use like a substitution thing, and you can solve it that way. You can now sort of substitute 2x for y over here. So 2x plus 3 times 2x equals 8. 2x plus 6x equals 8. 8x equals 8. X equals 1. Kind of interesting to get to this point where it's almost like a ratio between the two variables. We were able to get that by eliminating the constant. I bet you have not seen people eliminating the constant. They're often always eliminating either the x or the y. This might be something that you mention on the day after the test, or maybe something you never mention at all. It's up to you, but I find it interesting to see how different cultures, most teachers don't know because they haven't spent time studying the 9 chapters of the mathematical arts in ancient China to see how other cultures did it. But there are other ways to do it besides substitution and elimination. Okay, that's going to do it for the 4th lesson. The 4th video. The 5th video, I'll start to plan. I might plan like 1 lesson or 2 lessons, and then I'll show you how I make a test on this. Well, I hope you're enjoying this. It's already been 2 hours, and for someone who there isn't anything as detailed as this, maybe anything as boring as this that I've seen. So I hope someone's getting something out of it. See you next time.